Here we introduce some basic properties and metrics for social networks. What is a social network? The term social network is commonly used to mean a company or an app that connects people in a graph. But here we mean something more abstract, the actual graph metaphor for studying the relationships among a group of people. So we'll have nodes or vertices of the graph. Those will represent people. And various specific relationships between people will be represented by the edges or links between the nodes. So the whole system of people and their relationships will be the network or graph encompassing these vertices and edges. Here's a graph, for example, where the nodes are actors and the edges are movies they appeared in together. Or here's one where the nodes are people and the edges are social relationships like brother or friend. But for many questions, we can abstract away to just talk about the structure of these four nodes and these four edges. The fact that there's a link between 1 and 2 and 2 and 3 and 1 and 3, but no link, for example, between nodes 3 and 4. Networks can be undirected or directed. In undirected networks, the edges between nodes are symmetric. Things like friendship on Facebook or actor collaborations or Twitter conversations. In directed networks, however, the edges are asymmetric. They're arrows that point in a particular direction. So in citation graph, the nodes are papers, and the edges point, let's say, from paper 2 to paper 1 if paper 2 cites paper 1. Following someone on Twitter or Instagram is a directed relation. Let's introduce some useful properties of nodes. Two kinds of measures of how important or central a node is in a graph: node degree and node betweenness. And we'll also introduce the important clustering coefficient. The degree of a node I in an undirected graph is the number of edges touching I. So in this graph, node 2 has 4 edges incident on it. So we'll say the degree of node 2 is 4. Nodes 1 and 3 both have a single edge incident on them. And nodes 4 and 5 both have 2 edges incident on them. In a directed graph, we can measure a node's in degree, how many people point to it, or its out degree, how many nodes does it point to. For example, in this directed graph, node 2 and node 4 both have 2 people pointing at them, for node 2 and for node 4. Nodes 1 and 5 both have in degree of 1, 1 for 5, 1 for 1. And node 3 has an in degree of 0. Nothing points to node 3. Another kind of centrality is betweenness centrality. A node has high betweenness if lots of the shortest paths between pairs of nodes must pass through it. So for example, in this graph, the betweenness of node 7 is high because many of the shortest paths between pairs of nodes, like node 2 and node 11, or node 4 and node 8, must pass through node 7. The betweenness of a node A, we could also compute betweenness for an edge like AB, is the number of shortest paths that go through A, or AB if we're doing edges, divided by the total number of shortest paths that exist between all pairs of nodes. So out of all shortest paths between all pairs of nodes, how many of them go through the specified node or edge? So we can define B sub j, the betweenness of node j, as the sum over all pairs of nodes I and k that aren't j, out of the total number of shortest paths between I and k, how many of them pass through j, the number of shortest paths that go through j. Let's walk through the betweenness computation for this node B. For example, take the pair of nodes A and C. The shortest path between A and C is this short path, and it doesn't go through B. Of the one shortest path, 0 go through B. There are 2 shortest paths between A and D, both of length 2, and one of the 2, this one, goes through node B. So of the 2 shortest paths, one goes through node B. And of the one shortest paths between nodes C and D, that one does not go through B. So in sum, we have 4 shortest paths between all pairs of nodes that aren't B, and one of them goes through B. So that's a centrality of 1/4 or 0.25. Finally, let's introduce a very important property of a node called its clustering coefficient. The clustering coefficient for a node measures a property of its neighbors, the nodes that are adjacent to it, connected to it by an edge. How about I'll informally call its friends? So the clustering coefficient C sub A for a node A measures the percentage of my friends that are friends with each other, the percentage of the nodes adjacent to me that are also adjacent to each other. Let's compute the clustering coefficient for this node A. A has 3 friends, B, C, and D. So there are 3 possible links among those friends, BC, BD, and CD. Of those 3, only one exists, CD is in our real graph. So the clustering coefficient for node A is 1 out of 3. How about for node C? What's its clustering coefficient? Here there are 2 neighbors, A and D, and one possible link, the link A to D, and that link is in fact there. So the clustering coefficient is 1 out of 1, or 1. The clustering coefficient ranges from 0, no friends know each other, to 1, all the friends know each other. And here's the equation we've just described. If n sub A is the number of neighbors of A, out of the n times n minus 1 over 2 possible edges between those neighbors, what percentage of those exist? We've seen some important metrics for nodes in social networks, including their degree, betweenness, and clustering coefficient.